Greetings, I'm Justas Kardoka, and I'll present our article Building Heat Loss Evaluation using artificial intelligence methods and thermal photogrammetry. The authors are me, Justas Kardoka, and also Agne, Paulauskaite, Taraseviciene, and Darius Pupeikis. For a short overview, in the EU, buildings account for about 26% of all CO2 emissions, and most of these emissions are from the usage phase of the building and not, for example, from the construction or demolition stages. For preventing such CO2 emissions, it is important to be able to accurately evaluate them and the thermal losses of buildings. And in most cases, such evaluations require on-site expertise and or running certain simulations, which can be very costly. A common technique to evaluate these thermal losses is by using thermal cameras. And as you can see on the right in the slide, this is how a view from a thermal camera looks like, in which we can see the surface temperature of different locations in the image. And here, for example, we can see a cold bridge inside of a building. And using these thermal images, we can build photogrammetry models, which would be a 3D representation of a scene that's captured with a thermal camera. And although these thermal photogrammetry models are being actively developed, their use in calculating these thermal losses is not that widely researched, and it is a relatively new topic. In our work, we propose a methodology for calculating heat losses using thermal photogrammetry. And here you can see a small overview of our methodology, and I will go into each step in the following slides. Regarding our input data, we used a 362 images captured with a DJI Mavic 2 Enterprise drone, and the temperature values captured with the drone range from around -10 degrees to 200 degrees Celsius. And using these images, we created a photogrammetry model, which consists. We created a thermal photogrammetry model and then converted it into a point cloud. And this point cloud contains around 6 million points. And also what we can see is that in the point cloud, there is a lot of noise, like the ground layer and also vehicles on the right-hand side. Regarding the thermal images, they must be processed with the proprietary DJI software. For processing these images, we use the emissivity parameter of 0.95 as the default value. And we mapped the individual RGB values to surface temperatures, as you can see in the table. Regarding the processing of the thermal point clouds, we had to use algorithms for segmenting the building for which we want to calculate the heat losses. So we used different machine learning algorithms for that. We used the classic RANSAC algorithm and also two pre-trained deep learning models, KPConv and RunDaNet. And with these models, the best results were with the deep learning models. And for the metrics, we used standard metrics that you can see in many different papers, but also we used a chamfer distance metric, which is specifically developed for comparing different point clouds. The segmented buildings included a large amount of noise. As you can see, for example, on the right side, there are vehicles that still remained in the point cloud after buildings were segmented. And we used the statistical outlier removal to try to remove as much noise as possible. And the noise that we detected is colored red in the image. And removing these points increased the accuracy of the building model. With this data, we joined it by the RGB values in the thermal images and in the thermal point cloud. And as you can see, it results in a list where a mesh with specific area is assigned a surface temperature value. And this data can be used to calculate the heat losses of a building. Regarding the actual heat losses calculations, they were calculated by multiplying the surface area that we see in this slide with the heat transfer coefficient and the difference between outdoor temperature and indoor temperature. The heat transfer coefficient value used was 0.202, as it is a common value for wall materials. And regarding the indoor air temperature, since we do not know what was the actual indoor temperature of the building at the time when the thermal images were taken, we used a range of different values and performed the calculations on each of them. And from the results, we can see that the predicted heat losses are rather similar to the actual heat losses of the building, especially if you are not considering the ground layer, which is not captured in the thermal images and still has certain thermal losses. And the mean average error across all the indoor air temperatures for our predictions is around 0.42 and 0.14 kilowatts. In conclusion, although thermal imaging is mostly utilized nowadays in detecting certain thermal phenomena, like previously shown the cold bridges, they can also be utilized for a general monitoring of the thermal dynamics of a building. And by utilizing point clouds and artificial intelligence algorithms, we managed to calculate such thermal losses. And using our methodology, the results vary with a mean average error of around 0.14 and 0.42 kilowatts. In this topic, there is a lot of further work that can be done. The thermal losses could be calculated during, for example, the heating season, which we were not able to do due to technical reasons. Further work would also explore dynamically assigning the emissivity or the heat transfer coefficients, because different coefficients should be used based on the surface. For example, the windows of a building would have a different emissivity parameter or heat transfer coefficient. And that is it. Thank you.
Thank you very much. Okay, thank you. And now we have our next